So today we will start design of box culvert part 2 considering case 2, okay, which includes dead load, live load, effect of earth pressure and water pressure. That means when the culvert is running full, so there is water is flowing inside the culvert. So what will be the distribution of forces? So let's draw the distribution diagram. So this is the culvert A, B, D. So in the previous lecture, we have calculated this top loading, that is 57.85 kilonewton per meter square, and this bottom slab loading this is 72.85 kilonewton per meter square, and there will be the effect of earth pressure from outside, okay, and this value we have calculated. Here there will be the effect of water pressure in opposite direction from inside. Okay, so we can calculate this intensity of water pressure, that is intensity of water pressure will be how much? What is the expression? That is gamma W into H. Gamma W is unit weight of water, that is 9.8 kilonewton per meter cube, into height is height of the sidewall, that is your 3.3 meter. So we can calculate this 32.37 kilonewton per meter square. So intensity of water pressure is 32.37 kilonewton per meter square. That is here this is 32.37 kilonewton per meter square, and this one we have calculated. This part is 16.28 and this part is 20. Okay, so if we calculate the resultant forces at the top and at the bottom point, then it will be at the top this portion, the resultant force will be from the outside towards the wall, and this part will be, this is 16.28, so this will be 16.28 kilonewton per meter square, and at the bottom it will be this minus this, so this total is how much? this total. This is 20 plus 16.28. 20 plus 16.28 minus 32.37. So this one will be 4.46 kilonewton per meter square. This is the resultant force at the bottom. And so if we divide this again, so this part is now this part. This is how much? 4.46 kilonewton per meter square. Let's take this as W1, and this rest part, this will be 16.28 minus 4.46, which is equal to 11.28 kilonewton per meter square. Let's take this as W2. Okay, now we have to find out the fixed moment MFAB, MFDC, MFAT and MFD. So what will be MFAB? This is AD. MFAB will be due to the UDL, that is 57.85, that we have already calculated, minus WL square by 12. So minus 57.85 into 3.3 square divided by 12, that is equals to minus 52.5 kilonewton meter. Then MFDC. So MFDC will be 72.85 into 3.3 square divided by 12, that is equal to 66.11 kilonewton meter. Now come to MFAD, fixed moment for AD, this one AD. So we have divided this into two parts. One rectangular, that is uniformly distributed, W1, and another load 0 at the bottom, another triangular load, that is 0 at the bottom, and at the top is 11.82. So separately we have to calculate. So for this, due to this, it will be WL square by 12. So that is 4.46 into 3.3 square divided by 12 plus, so for this type of load, this will be WL square by 20. WL square by 20, that means W2 11.82 into L square by 20. So this one is coming 10.5 kilonewton meter. Now come to MFDA, it will be just the reverse one, minus 4.46 L square by 12 minus 11.82 is W2 L square by 30. Okay, so if you calculate, this will be minus 8.34 kilonewton meter. Now I'll calculate the total moment. So I'll use this moment distribution method. Moment distribution method. So there are two joints D and A. So here the members are DA, DC and DA. Here AD and AB. So what is the distribution factor? We have already calculated in the previous video. For DC, this is 2 by 3, this is 1 by 3, this is 1 by 3, this is 2 by 3. The fixed end moment we have calculated for DC 66.11 kilonewton meter, dA minus 8.34 kilonewton meter. For AD, this is 10.5 and this is minus 52.5. Then what is the balance moment? This plus this into 2 by 3. So that will be minus 38.51. This one minus 19.25. Then this is 14. This is 28. Now come to carryover moment. This is fixed end, so this will be 0. This is fixed end, this will be 0 for this. 14 by 2, 7. And this minus 19.25 by 2, minus 9.625. Again the balance moment 0.7. 0 plus 7 into 2 by 3, and that will be negative, so minus 4.66. 0 plus 7 into 1 by 3, that is minus 2.33. Then this one 3.2 and this is 6.41. Now next carryover moment, this is 0. This will be 3.2 by 2, that is 1.6 minus 1.15 again 0. Now the balance moment, this is the balance moment. 0 plus 1.6 into 2 by 3, so minus 1.06. This one minus 0.533, and this is 0.388. This is 0.776. Now what is the carryover moment for this? It is 0. 0.388 by 2, 0.194 minus 0.266. This is 0. Now what is the balance moment? 0 plus 0.194 into 2 by 3, that is minus 0.129. This is minus 0.064. This is 0.088. This is 0.177. Now what is the carryover moment? This is 0 for this, 0.044. This is minus 0.032. This is 0. Next the balance moment, minus 0.029 minus 0.014. This is 0.01, 0.021. Carryover moment, this is 0. 0.005 minus 0.007, 0. Again the balance moment, minus 0.003 minus 0.001, 002, and this is 0.004. So let's stop here. What is the total fixed end moment for this? This is 21.79. This is minus 21.7. This is 17.1. This is minus 17.0. So our calculation is okay. This is equal to this. This is equal to this. Now we'll calculate the net bending moment. Net bending moment at here E and F and in the sidewall. So for span AB, what is the free end moment? Free end moment at E. This is WL square by 8, that is 57.85 into 3.3 square divided by 8, which is equal to 78.74 kilonewton meter. So what will be the net bending moment at E? 78.74 minus the fixed end moment that I have calculated, 17.1 or 17. That is equal to 61.74 kilonewton meter. For span CD, so the free end moment at F is equal to 72.5 85 into 3.3 square divided by 8, which is equal to 99.16 kilonewton meter. And what is the net bending moment at F? This is equal to 99.16 minus fixed end moment. We have calculated 21.7. So this is equal to 77.37 kilonewton meter. Okay. Similarly, next span AD is a sidewall. So for the sidewall, what is the free moment at the mid span? Free moment at the mid span will be WL square by 8 plus WL square by 16. So W1, that is W1 L square by 8 plus W2 L square by 16. W1 is the uniformly distributed load. So W1 L square by 8, and for triangular this is W2 L square by 16. So W1 is how much? 4.46 into 3.3 square divided by 8 plus W2 we have calculated 11.82 into 3.3 square divided by 16. So this will be 14.11 kilonewton meter. What will be the net bending moment at the mid span? This will be so at the bottom it is 21.7, at the top it is 17.2. So 17.1 or 17. So 17 plus 21.7 divided by 2 minus, this is a fixed end moment, minus 14.11, which is equal to 5.24 kilonewton meter. This is for sidewall maximum bending moment, that is at the center. So let's draw the diagram. This is A, B, C, D. So this is 4.46. This is the resultant distribution of pressure. This is 4.46, and here this is 4.46 plus 11.82. So total is, so if we do this, okay, so this is 4.46, this is 11.82. So what we have calculated, the fixed end moments, this is 17, this is 17, this is also 17, 21.7, 21.7, this is also 21.7. This is symmetrical, so this side will be same as this side. So let's draw the bending moment diagram. Okay, so this is 21.7 kilonewton meter. Then this is 17 kilonewton per meter, 17 kilonewton meter. Similarly, this side, this is 17, this is 17, 21.7, this is 21.7, and the maximum minimum, this is E, this is F. So at this point we have calculated 61.74, this one, and at F 77.37 kilonewton meter, and here this is 5.24. Okay, so this is the maximum bending moment for case 2. Now we'll move to this case number 3. So here we'll consider the dead load, the live load, the water pressure, and the lateral earth pressure due to the dead load only, without considering the live load. Means there is no vehicle. The lateral earth pressure will be only due to the dead load. That may be a case. So you can say this earth pressure due to dead load only. We won't consider the live load. Means when there is no movement of vehicle over this culvert, that may be a case. So if this is the case, so we have to calculate so what is the lateral earth pressure due to the soil, that is Ka into gamma h. So K we will already calculated 1 by 3 coefficient of active earth pressure into 1 minus sin phi by 1 plus sin phi into gamma of soil. Unit weight of soil is given 18 kilonewton per meter cube and height is 3.3 meter. So this is coming 19.8, or you can say 20 kilonewton per meter square. This thing we have already calculated. Now to this we will add only the surcharge due to the dead load only. Okay, lateral surcharge due to the dead load only. We won't consider the live load part here. So that is K into Q. So K is 1 by 3 and dead load is 14, which is given. This is 4.66 kilonewton per meter square. And what is the water pressure? Because the culvert is full, so this will be gamma W into H. So 9.8 into 3.3, which is equal to 32.34 kilonewton per meter square. Okay, now what will be the total pressure at the bottom and what will be the total pressure at the top? So as you know, at the top, okay, first we will draw this diagram. Okay, So here we'll have this surcharge loading, that is KAQ, this one 4.66, plus there will be this lateral earth pressure, which will be a triangular load. So this part is how much? 20. Okay, so this whole will be 20 plus 4.66, 24.66. 24.66, and the culvert is full, so there will be opposite pressure due to the water, and this one is 32.34, and here it is 0. So the same thing this side. Okay, so we can calculate this total pressure at the top. This will be 4.66 plus 4.66 due to the surcharge, dead load surcharge, and due to this lateral earth pressure at the top, this is 0, and here also due to the water, this is 0. So total 4.66. And at the bottom, due to the surcharge 4.66 plus due to the lateral earth pressure, that is 20, minus due to the water, that is 32.34. So total will have 7.87 kilonewton per meter square. Okay, that means if you draw the resultant of this, it will be at the top 4.66, 4.66 this side, and at the bottom this total is 7. Actually this is minus 7.87. So let's calculate in other way. Okay, we will keep this 4.66. This is 4.66 and this is 4.66, and so at the top this is 4.66 alone, but at the bottom, apart from this 4.66, we'll have one your earth pressure, lateral earth pressure of 20, and in opposite direction we'll have a this water pressure 32.34, which is more than the earth pressure. So the resultant will be in the opposite direction. Okay. The resultant will be in the opposite direction. So in the opposite direction we'll have a pressure like this. Here this is 0, and here this is 32.34 minus 24.66, which is equal to this will be around 12.54 kilonewton per meter square. Let's take this W1, uniformly distributed and triangular load. This is W2. Okay, now what will be the fixed end moments? MF AB that is same as previous, WL square by 2L. So minus 52.5 we have already calculated in case 2. Then MFDC, this is same as the previous, plus 66.11 kilonewton meter. Then MFAD, this will be W1L square by 2L plus, sorry, minus W2L square by 30, which is equal to W1 means 4.66 into 3.3 square divided by 12 minus W2 12.54 into 3.3 square divided by 30. So final, this is coming minus 0.32 kilonewton meter. Then MFDA, just the reverse one, will be minus 4.66 into 3.3 square divided by 12 plus 12.54 into 3.3 square divided by 20. So this is equal to 2.6 kilonewton meter. So now I'll go for moment calculation by using moment distribution method. So these are the joints D and A. Remember DC, DA, AD, AB. So what is the distribution factor for DC? 2 by 3. This is 1 by 3. This is 1 by 3. This is 2 by 3. Then the fixed end moment 66.11. This is 2.6. This is minus 0.32. This is minus 52.5. Next, what is the balance moment? So this will be 66.11 plus 2.6 into 2 by 3, negative minus 44.07. This is minus 22.9. This is 17.7. 17.7 and this is 35.21. Now carryover moment, this is fixed end, so 0, and this will be 17.7 by 2, 8.85. This is minus 22.9 by 2, minus 11.45. This is 0. Balance moment, this plus this into 2 by 3, minus 5.9, minus 2.95, 3.8, 7.63. Now the carryover moment, 0, 3.8 by 2, so 1.9, minus 1.48, 0. Balance moment, minus 1.27, minus 0.63, 0.5, 1.0. Carryover moment, 0, this is 0.5 by 2, 0.25, minus 0.325, 0. Balance moment, this will be minus 0.17, minus 0.08, 0.11, 0.22. Carryover moment, 0, this is 0.055, this is minus 0.04, this is 0. Balance moment, minus 0.037, minus 0.018, this is 0.013, this is 0.027. So let's stop here and calculate the total. This is 14.663 minus 14.9, 8.52 minus 8.41. Now you can repeat the same procedure. Free end moment at E we have already calculated, that is 78.74 kilonewton meter. In case 2 that will be same. So the net bending moment at E will be 78.74 minus 8.41, that is 70.24 kilonewton meter. Similarly, for the bottom, what is the free end moment at F? We have calculated 99.16 kilonewton meter. So the net bending moment at F, 99.16 minus 14.6, so 84.56 kilonewton meter. Now for this AD, what is the midspan moment? Midspan moment will be W1 L square by 8 plus W2 L square by 16. So what is W1? 4.66, 3.3 square divided by 8 minus 12.54 into 3.3 square divided by 16. This one minus 2.18 kilonewton meter. The net bending moment is equal to the F is a fixed end moment, that is 8.5, 14.6 by 2 minus of minus 2.18, which is equal to 13.73 kilonewton meter. Okay, so now we can draw this. This is the resultant diagram, pressure diagram. Okay, this is A, B, this is C, this is E, this is F. So these are the moments. It is 8.5, this is 8.5, 14.6, 14.6. Similarly this side. And this loads are this loads. This is how much? 4.66 and this is 12.54. Draw this. Five, 8.5, this is 8.5, 8.5, and this is 14.6, 14.6, and this term, this is how much? 70.24. This one, next is 84.56, and this is 13.73. This one. So next is we have to choose out of these three cases. We have to choose the value of maximum bending moment at each point. Okay, so for top slab, first we will consider this top slab. This is case 1, case 2 and case 3. So for case 1, what is the bending moment at center, that is at point E? case 1, this is 51.37. We have calculated in previous video. For case 2, 61.74 kilonewton meter. For case 3, 70.24 kilonewton meter. And what is the bending moment at end? That is MAD. This is also in kilonewton meter. This is 27.37 kilonewton meter. We have calculated in the previous video. And for case 2, this is 17.09 kilonewton meter. For case 3, it is 8.54 kilonewton meter. So out of this 3, we have to choose the maximum value. Okay. So this one we will take. So assuming, now we have to assume the depth of the slab. Assuming a depth of 300 mm and the effective cover is equal to 40 mm, and we'll use this diameter of bar 20 mm. What is the effective depth? 300 minus 40 minus 20 by 2. Sorry, this is your clear cover. So this is coming 250 mm. Now we'll do this check for tap. This thing we have already taken. Next we will check whether this much of this depth of top slab is adequate to resist this moment or not. So check for depth. Mu is equal to QBD square. Q is 0.36 XU max by D into 1 minus 0.42 XU max by D into FCK. This is value of Q and BD square. So you can calculate this Q value. Q will be for FE 415, this Q value will be 3.45. Okay, so D will be mu divided by QB root over, which is equal to 70.24 into 10 to the power 6 divided by 3.45 into B is 1000. So this is coming 142.64 mm. This is the required depth, D required. Okay, but we have taken 250, which is more than this, so this is safe. Okay, so if this depth is safe, then we can go for calculation of area of steel reinforcement. For this is for top slab. For top slab, which is mu is equal to 0.87 FYSD into 1 minus FYSD divided by FCKBD. Okay, so from this we can calculate the area of steel. So maximum moment will take 70.24 into 10 to the power 6, 0.87, Fy is 415, D is 250, 1 minus 415 is D, FCK is 25, B is 1000 into 250. So area of steel from this is 822.64 mm square. So let's take 830, round figure. This is at E point. Okay, Now we can calculate the spacing of bars. Spacing, that is for 1 meter width we'll finding 30 divided by pi by 4 20 square. This is 378 mm. So spacing we can take less than required, that will be safe. So let's take 300. So finally we'll provide 20 mm dia bar at a rate of 300 mm center to center spacing. Okay, now what is the distribution still? What is the distribution still perpendicular to this? So area of the steel required minimum area will provide, that is 0.12% of the cross sectional area, that is P into D, 1000 into 300, which is equal to 360 mm square. So if you take 8 mm dia bar as distribution reinforcement, what will be the spacing for 1 meter width? Required area divided by area of single bar is equal to 130 mm. So let's take 130, it will be safe. So let's provide 8 mm dia bar at a rate of 130 mm center to center spacing as distribution reinforcement. Okay, so whatever we have calculated here, this is for to resist 70.24 kilonewton meter for this, which is bending moment at the center. So now we can find for the end, which is less than that. This is centered at E point. This is also at E. Now consider what is the bending moment at support. 27.36 kilonewton meter. Okay. So what will be the area of steel? .87 Fy AST D 1 minus Fy AST divided by FCK BD. So let's calculate the area of steel for this. This will be 309.4 mm square. So let's take 310. Now again, at the support we have to bend half of the bars. So half of the main reinforcement, so what is the main reinforcement amount? This is the main reinforcement at E, and the amount is how much? 830. So half of this main reinforcement, so like this, if this is the top slab where we'll provide this reinforcement, So half of the main reinforcement, so this is the center point for which we had designed. So we can bend half of the bar, each alternate bars like this at the support, because the 70 that reinforcement, that moment, that is at the center, so we had designed for that, but at the end that much of moment is not required, so we can bend half of the bars here. Okay, so half of the main reinforcement means that is 830 by 2. This is bent at the support, 830 by 2, so 415 mm square. This much of bar we are bending at the support. So we have already this much area of bar at the support, and what is the required area at the support? 309. So this is more than 309, which is already present at the support, so no need to provide some extra reinforcement at the support, because we have already reinforcement, already the required reinforcement. Required enforcement at the support. So no need to provide extra reinforcement. At the support. So this is over. This top slab is over. Similarly we have to design for bottom slab. Similarly we have to design for bottom slab. So what are the cases? Case 1, case 2, case 3. This is the bending moment at F, that is at the center, and another at the end at point D. So what is the calculated bending moment? We have calculated it in this 63.9, 35.2. We have calculated in previous video, part 1, and for case 2 this is 77.4, this is 21.7, this is 84.5, and this is 14.63. All are in kilonewton meter. So there is the maximum value, this, and here this. So same, we'll assume depth, overall depth 300 mm, then clear cover 40 mm, then diameter 20 mm. So effective depth will be 300 minus 40 minus 20 by 2 is equal to 250 mm. Then what is the D required? That is A mu by QB root over, so this is 84.5 written to the power 6 divided by 3.45 into 1000. So this is coming 156.5 mm, which is less than 250 mm. So this is safe. This depth, whatever we have assumed 250, this can carry the moment of 84.5. If it can carry this 84.5, so it can carry all other loads. So now I will calculate area of steel. Area of steel at the center, F. Center of bottom slab, that is F. So same process, 84.5 into 10 to the power 6 is equal to 0.87 FYSTT into 1 minus FYST divided by FCKBT. Okay, just put the expression, we'll get a area of steel 1011.41 mm square. So let's take round figure. Now you can calculate the spacing for 1 meter width. This is coming 308, so let's take 300 mm. So provide 20 mm dia bar at a rate of 300 mm center to center spacing as main reinforcement. This is at F, center of bottom slab. Now come to the distribution reinforcement. This will be same as the previous. The minimum amount we have to provide is distribution reinforcement, that is 0.12% of BD. So this is 360 mm square. So this will be same as the previous case, that is at the top case. So let's provide 8 mm at a rate of 130 mm center to center as distribution reinforcement. Okay, now come to the support. At support, what is the bending moment? This is 35.2. 35.2. So let's check what is the area of steel required. 35.2 into 10 to the power 6 is equal to 0.87 FISTT 415 ASTT into 1 minus FIST divided by FCKBT. So we can calculate the area of steel. This is 400.6 mm. Now we'll check whether we need to provide some extra reinforcement or half of the main bar is enough to take this moment. Okay, so what is this is how much? 1020. Okay, so 1000. Sorry, this is 1040. 20. Okay, 1020 divided by 2. This is 510 mm square. So this much amount of steel is already present at the end, and this is the required amount. So this is more than the required amount. Okay, so no need to provide the extra reinforcement at the support, because we are bending this main bars at the support. Each 50% of the alternate bars we are bending. Okay, so that can take the negative moment at the support. Now come to the sidewall. For this sidewall we have to design like a column. Okay, so this is 57.55 kilonewton meter and this is 72.55 kilonewton kilonewton per meter square. Kilonewton per meter square. So this side wall we have to design it like a column. So for this we have to refer SP16 for interaction diagram. For interaction diagram. So what will be this axial loading? Axial loading on this column. Okay, so we'll calculate this reaction at A and D. So for A, if V is the reaction at A, it will be how much? So reaction at A here, this is B, this is C, which is equal to reaction at B. So this is uniformly distributed load. So 57.55 into 3.3 divided by 2, which is equal to around 99 kilonewton. Similarly, here D and C, V at D is equal to B at C, which is equal to 72. This is 85. 85 into 3.3 divided by 2 is equal to 120.2 kilonewton. Okay. So these two reaction forces, it's the same for all the three load cases. So out of this two, you have to take the maximum value, that is 120.2 kilonewton. So what will be the factor axial loading, that is denoted as Nu. So let's multiply this factor of safety, it is 1.5. This will be 180.30 kilonewton. Similarly, we have to calculate this M value. What is this? This is Nu, and the moment for case 1, this is 35.66. Case 1, 21.79. Case 2 and 14.66. Case 3. Case 3 you can check here. See, this is 14.63 for case 3. So out of this 3, you have to take this maximum, because at the bottom we got this maximum reaction force, so moment will be maximum at the bottom. So for bottom case, these are the, for bottom slab, these are the end moments, 35.2 for case 1, 21.7 for case 2 and 14.63 for case 3. So out of this 3, you have to take the maximum value, that is 35.66, and the factor value will be 1.5 into 35.66, which is equal to 53.49 kilonewton meter. Okay, so now to refer this interaction diagram, we need to find out this two factors, that is Nu by FCKBD and that mu by FCKBD square. Okay, so let's calculate. This is 180.3 multiplied into by 3. This is in Newton. This is 25, B is 1000, and this is 250. So this is coming 0.024, and this one 53.49 into 10 to the power 6 converted into Newton mm. 25,000 to 250 square. Sorry, this is 300 overall depth. So this factor is coming 0.023, Now to refer this interaction diagram, we need this Fy is 415, then this d dash by d, which is equal to 40 by 300, so this is 0.13. So we don't have this diagram for 0.13, so let's take 0.15. Now from SP16 and this page number 118 you can refer, 118 interaction diagram. The corresponding value of Nu by FCKBD and Mu by FCKBD square is equal to the corresponding value of P. P by FCK you can get from here this as 0, where P is the percentage of steel. Okay, so if this is 0, if this is coming 0, then we can provide this minimum reinforcement at the sidewall. So for column, what is the minimum reinforcement? 0.8% of the cross-sectional area as per IRC 456. So we can calculate this value, 1000, this is 300, this is coming 2400 mm square. Okay, so if you provide 20 mm dia bar, what will be the spacing? 1000 divided by 2400 pi by 4, 20 square. This is equal to 130.33. So let's provide 130 mm. So let's provide 20 mm dia bars at a rate of 130 mm center to center spacing. This is to be provided in the sidewall. Okay. Now the most important is the detailing. So we have to show the detailing. Okay, so this is the reinforcement, and we have to bend each alternate bars. So next bar, one bar will be like this, and each alternate bar we are bending here. Similarly here also. So first bar will be like this, second bar, and this is the main bar, and the distribution bar we can provide reinforcement here. Similarly this side also. This side also. And these are the distribution bars perpendicular to the main bar. Okay, so this length, this is 3.3 meter, width of the support, this is 300 mm, width of its bottom slab and top slab, and also this sidewall. and you have to bend half of the bar, and this distance from here, this is L by 5, which is equal to 3300 by 5, 660 mm. So this is also 660 mm. And these main bars, these are the these are 20 mm dia bars at a rate of 300 mm center to center, and this distribution these are 8 mm at a rate of 130 mm center to center. Sorry, this column one, this is this column part, this is 20 mm at the rate of 130 mm center to center. Okay, like this we have to show all the detailing. Okay, so thanks for watching. Do like, comment and subscribe.